So there's a question in the chat from Jaideep whether you can ask a couple of questions regarding your last lectures. Do you want to start with it now?
Sure, we could start with it briefly now, and yeah.
Okay. Okay. Maybe I can just. Okay. So there's a bunch of questions that is there in the chat. Do you want me to read it?
Oh, if you don't mind, I don't know how to access chat when I'm on full screen.
That's okay. Yeah. Okay. So the first question is that in flat space, the Regge limit is s tends to infinity with t less than 0 fixed.
Yes.
Is that the same for the CFT case as discussed last time? And if yes, then how?
You know, in CFT, what we're doing is the following. We're taking sigma to 0. Okay. So CFT, if you want to be precise, CFT is in terms of CFT variables, right? So we have to talk about what's happening in the cross ratio space. So the precise statement is the following. If you go to this, oops. Here. Suppose you go to this Z bar sort of plane. Okay, what we're doing in CFT is that you start somewhere in Euclidean space. When Z goes to 0, just directly towards 0, but Z bar goes to 0 like this, after going around this one thing. So in CFT, you're taking sigma to 0. You remember Z was equal to sigma e to the power rho, and Z bar was equal to sigma e to the power minus rho. So what you're doing in CFT is to take sigma to 0, holding rho fixed.
Okay, so there's a second question, which is, does the coefficient of bulk point singularity give us only the tree-level S matrix or the full S matrix?
What, sorry?
Does the coefficient of bulk point singularity in ADS, does it give the tree-level S matrix or the full S matrix?
Does the coefficient of the bulk? Okay, excellent. So good. That's a good question. The arguments that have been made precisely so far are for the tree-level S matrix. Okay. Now, it seems to me that it's likely that these arguments will generalize order by order in perturbation theory, in 1/n perturbation theory. Though even that is, you have to think a little bit about it. The question is whether the loop has important contributions that go far away, like IR kind of divergences. In the absence of IR kind of divergences, I think that that there's a good chance that this will generalize order by order in perturbation theory. However, this has not been studied in detail. What is well understood is for, I would say, is for the tree level S matrix. And now you can ask, what about non-perturbatively? Now, or even tree level including stringy corrections. Now, that's interesting. Both non-perturbatively as well as tree level using stringy corrections, we know that the bulk point singularity gets smoothened out. Okay, and so this bulk point singularity is really a large n large lambda artifact that does not really exist at finite n or finite lambda. I should say this a little more precisely. Conformal blocks independently on the scattering sheet have a singularity at rho equals 0. However, they have a weaker singularity at rho equals 0 than those that come from this bulk point singularity. So the story is a little involved, and but morally speaking, okay, there's something inaccurate in what I'm saying now. But morally speaking, the bulk point singularity is washed away by finite alpha prime and finite G string effect. Certainly, black hole formation, or amelioration of the growth of string scattering amplitudes by alpha prime effects wash this thing away. It leaves a residue of the singularity, but a much weaker one. Sorry.
And the last question is, does your analysis depend on whether the dual scalar in ADS is massless, or does it hold for massive scalars as well?
Okay, for scalars, it holds for massless and massive scalars, provided the mass is, of order 1 in ADS units. Okay, and the analysis basically doesn't really care about the mass. However, the question here is more interesting for vectors and for gravitons. Okay, at least as presented, the analysis here holds for vectors, for gauge fields, and for gravitons only for massless gauge fields and gravitons, at least as presented here. And the key complication, now you might ask, you might think this is weird. Why does the analysis extend easily to massive scalars, but not extend easily to massive gauge fields or gravitons? And the reason for this is, of course, gauge invariance. You see, there's a discontinuity between massive and massless gauge fields. Massive gauge fields have one more degree of freedom than massless gauge fields. They have these longitudinal polarizations. Now, if it was just a change in number of degrees of freedom, that also by itself would not do much. But what makes this analysis more complicated is the following. As you may know, longitudinal polarizations are much more strongly coupled than their transverse counterparts at very high energies. And the reason for this is the following simple physics fact. You see, if we're in a let's say a gauge boson has a longitudinal polarization because it has a mass. If we're in a situation where the mass is negligible, as is the case at very high energies, then the Lagrangian is approximately gauge invariant. So the degree of freedom that was making up the longitudinal polarization is approximately a gauge symmetry, by which I mean it approximately does not appear in the action, because a gauge degree of freedom does not appear in the action. The precise version of that is that it appears in the action, but with a coefficient that's very small. And anytime a degree of freedom appears in the action with a coefficient that's very small, its fluctuations are not suppressed by action terms, and therefore it's very strongly coupled. So the fact that the longitudinal polarizations become very strongly coupled at high energies, but remember this bulk point singularity happens because we're doing high energy scattering, and it gets its dominant contribution from high energies. So the fact that these longitudinal polarizations are extremely strongly coupled where this bulk point singularity is happening complicates the analysis a lot. Technically what it means is that a single term for massive gauge fields would not have a single bulk point singularity, but bulk point singularities of decreasing intensity. The most intense will be the one corresponding to the scattering of longitudinal polarizations. Then there would be a less intense one corresponding to the scattering of 3 longitudinal and one transverse polarization, and so on. So you'd have to unravel that structure completely in order to completely decode the S matrix from this bulk point singularity. It's a more complicated structure, and while it's plausible that this could be done, it's never been done. So the analysis that I presented is for massless gauge bosons and gravitons.
Okay. Yeah. So I don't see any further questions. So maybe we can start.
Okay. Excellent. You remember where we were at the end of last lecture. We had this CRG conjecture, which was going to be the physical constraint we were going to use to try to constrain S matrices. Okay. Now we've got the really conceptually important part in our hands, the CRG conjecture. However, we need the second part, which was to parameterize classical scattering amplitudes. We need the analog of the statement that CMZ had, which is that all gravitational scattering amplitudes are sum of 3 structures. Okay, and this is what we're going to try to understand in today's lecture. Today's lecture, is going to have parts that are technical, but hopefully there will be parts that are physicsy and fun, and hopefully it will not be too boring. Okay, so how do we parameterize S matrices? So we're going to focus on scattering of gravitons. Gravitons are massless, so they all obey the equation pi squared is equal to 0. All S matrices obey momentum conservations. Sum over pi's is equal to 0. And as all of you know, there are 3 natural invariants that you can build out of momenta that square to 0 or square to anything particular, and also obey momentum conservation. These are S, T, and U, which are minus of P1 plus P2 the whole thing squared, minus of P1 plus P3 the whole thing squared, and minus of P1 plus P4 the whole thing squared. And as all of you also know, the fact that these gravitons are all massless, well, for every mass, there's some relationship between ST and U. So there are only two independent pieces of data in scattering momenta for 4 particles. But the precise form of the relationship between ST and U, because the gravitons are massless, is S plus T plus U is equal to 0. Great. Now, when we're scattering gravitons, we also have to deal with polarizations. Okay. So to get into this, so our scattering data is not parameterized just by momenta, but it also needs to keep track of polarizations. So to get into this a little slowly, let's see first how this works for gauge bosons, which also, for which you also need to keep track of polarization data. Okay, so suppose the plane wave of a gauge boson is epsilon and I mu times e to the power minus I k dot x. I here is the particle index. Okay, so if the ith particle, a mu takes this form. Okay, now we could always choose to work in Lorentz gauge. Del mu a mu is equal to 0. If we work in that gauge, then this epsilon here obeys the condition ki dot ei is equal to 0. This is a very convenient gauge. It's also the gauge that string theory in the worldsheet formalism naturally uses. And it's the one we will adapt. It manifestly preserves Lorentz invariance. Of course, this gauge condition does not completely fix gauge invariance. There's a residual gauge invariance, and the residual gauge invariance is that if you take epsilon I and shift it by pi, the momentum of this moving particle, that leaves this gauge condition unchanged because this should have been ki, because pi dot pi or ki dot ki is equal to 0. Okay, and you can do this with any function of pi behind you, right? So we can do it with different zetas for different pi's. Okay, this is a gauge invariance of the problem. Now, since the 4 particles are scattering with different momenta, and since zeta could be a function of pi, effectively our S matrix has the following invariance: epsilon I goes to epsilon I mu plus zeta I pi mu, where zeta I are 4 completely independent numbers because they're zeta evaluated at p1, p2, p3, and p4, and there's no connection between these. So our S matrix, whatever it is a function of these polarizations. It's linear in each of the 4 polarizations. But it's not completely unconstrained. It has this invariance. Under the shift, epsilon goes to epsilon plus a shift in p and a separate shift in p for each of the 4 scattering momenta. Our S matrix must be invariant. Great. So the data for gauge boson scattering is the momenta and the polarizations. Polarizations are orthogonal to momenta and also are only physical up to these shifts. What's the deal with gravitons? Okay, so let's say that we start scattering a graviton. So a graviton is some plane wave that looks like this. We can use some sort of effective Lorentz gauge. And if you add into this, the Einstein equation along with this Lorentz gauge condition, it tells you that the Lorentz gauge condition is the condition that pi is orthogonal to hi. That's just del mu h mu is equal to 0. I, once again, is a particle index. And the Einstein equations force hi mu mu is equal to 0. So gravitons are traceless symmetric tensors. Okay, at the moment this looks like they're traceless symmetric tensors in d-1 dimensions because they're orthogonal to one direction, namely the momentum. However, as you know, there is this residual gauge invariance, which effectively is going to make them traceless symmetric tensors in d-2 dimensions. Okay. Now, to deal with this residual gauge invariance, it's useful to make a choice of polarizations. It's useful to make a choice of polarizations, that is to choose your polarization to be of the form epsilon mu, epsilon mu. Now, this you might think is a bit strange. Of course, epsilon mu I, epsilon nu I with epsilon dot epsilon is equal to 0 is a good polarization. It obeys all our conditions. It's symmetric and it's traceless. And if we set ki dot epsilon I is equal to 0, it will also obey this condition that h dot p is equal to 0. That's fine. But you might be worried that by making this choice, we're losing generality. Because surely not every symmetric traceless tensor can be written as epsilon times epsilon. And that's true. However, remember the S matrices are linear functions in H. Now, suppose you want something of the form epsilon 1, epsilon 2 plus epsilon 2, epsilon 1. You can get that as epsilon 1, epsilon 2 square. I'm calling this II structure square. It's not really accurate. It's tensor product, but okay, you know what I mean. You can get that as epsilon 1, epsilon 2 square minus epsilon 1 square minus epsilon 2 square. So if you wanted the scattering amplitude for what a graviton was doing in the polarization epsilon 1, epsilon 2 plus epsilon 2, epsilon 1, all you have to do is to compute the graviton scattering amplitude with the polarization epsilon 1 plus epsilon 2 and then subtract it for epsilon 1 squared, for epsilon 1 and epsilon 2. So you don't, and then every polarization can be written as linear, every symmetric polarization can be written as a linear combination of epsilon 1, epsilon 2 plus epsilon 2, epsilon 1. Okay, there's one point here I've brushed over in the argument, but it's basically correct. And so, you know, if you know the answer for polarizations of this form, you don't lose any generality. Okay, once you have the answer for the polarizations of this form, it's easy just to get the answer for the most general H. Really, basically, every time you see an epsilon I, replacing it by an H mu nu I. Okay, so this is a convenient thing, convenient choice, and choice that's widely made in the study of S matrices, is to keep your epsilons, your two epsilons for the gravitons the same. And in doing that, you don't lose any information. And basically, the reason for that is that your polarization was symmetric. Okay. Now, this is a large gauge invariance here because it's parametrized by a vector field rather than a scalar, as you know, the zeta, which was a scalar here. But if you want to preserve this choice of polarizations, you want your polarizations to remain of the form epsilon I times epsilon I, then you can't use this full gauge invariance. The only gauge invariance that you're allowed to use is epsilon I goes to epsilon I plus zeta I times pi mu, where the zeta I was this thing. So basically, epsilon I goes to hij goes to h mu nu goes to h mu nu plus p nu zeta. Okay, so it's a very similar kind of graviton gauge invariances that preserve this form of polarization are very similar to those for the gauge boson. And so in the end, graviton scattering amplitudes are bilinear functions of 4 epsilons. So separately bilinear in epsilon 1, epsilon 2, epsilon 3, epsilon 4. They're also functions of the momenta, and they have to share, epsilons have to square to 0. That's the only really new element. Apart from them being bilinear rather than linear, and the epsilon scattering amplitudes have to be invariant under this shift, the same shift as for photons. So you know, once you make these choices, graviton and photon S matrices become kinematically quite similar objects. Okay, so that was a brief discussion about the elementary kinematics of graviton scattering amplitudes. Okay. Now, in these lectures, we're not going to look at the most general graviton scattering amplitude. We're only going to look at classical graviton scattering amplitudes. What does that mean? It means graviton scattering amplitudes whose singularities are poles, if at all. Therefore, we're also going to restrict ourselves to those amplitudes that are generated by Lagrangians with a finite number of derivatives, finite number of terms, and also all intermediate particles are finite in number. Okay. This is a restriction, and it would be great to get rid of it. But at the moment, this is what we do. Okay, what does that mean for S matrices? For S matrices, it means that S matrices, or the analytic structure of S matrices that we're going to study, are poles plus a finite number of poles plus polynomials. In momenta, of course, all S matrices are always polynomials in epsilon. They're always linear for gravitons, quadratic, separately in each of the epsilons, polynomials in epsilon. Okay, so when I say polynomial, I always mean in momentum. Okay, so what we have to do is separately classify, try to write down as explicitly as possible all possible pole contributions to graviton S matrices and all possible polynomial contributions to S matrices. So this is what we're going to try to do now. Let's first start with the poles. Okay, you might have thought that the poles were the harder thing because they were singular, but actually the poles are the easier thing. Why are the poles easier? The poles are easier because, you see, how do you get a pole? You get a pole because two gravitons come and scatter, then they go in another particle, and that particle becomes two other gravitons. So you see that from this way of thinking of it, it's immediately clear that poles are classified by two things. A, the particles that can scatter, that two gravitons can scatter into, and B, the 3-point couplings of the two gravitons scattering into these particles. Okay? Now, what are the poles that gravitons can scatter into? Well, those are any irreducible representations of the little group, all allowed particles. This we all know, right? From the times we're undergraduates, we know how to classify particles using group theory. So the set of allowed scattering objects is well under control. Okay? The set of 3-point functions is a very simple object. I told you that when you try to write down all possible 3 graviton scattering amplitudes, this thing that went into the CMZ analysis, so a sum of 3 possible structures. So always true, the 3-point functions, 3 particle scattering amplitudes are a sum of a finite number of structures. Okay, so if we could just get complete control over the 3 particle scattering amplitudes and get complete control over, well, all particles, we already have that. So get complete control over the 3 particle scattering amplitudes, we've effectively completely classified the pole type scattering amplitudes. Okay, so let us go through a little brief exercise, maybe 5 minutes, on understanding how we can classify all 3 particle scattering amplitudes. So the particles that we're interested in, 2 graviton going to some other particle. For concreteness, for this discussion, I'm going to make that particle massive. Okay, so let me try to classify all scattering amplitudes of particle with a massive particle. Okay, massless case is actually more difficult for a number of reasons, including the fact that massless particles often have their own gauge invariant. So we put that aside for now. So 2 gravitons going to a massive particle. Okay, so let's do this classification. In order to do this, actually, it's very, very easy. So I'll just run through the logic just to see how easy it is. Okay, see, we've got these 2 particles scattering and going to a 3rd particle. So there are 3 momenta in the game, but these 3 momenta obey momentum conservation. So effectively, there are 2 linearly independent momenta in the game. These 2 linearly independent momenta define a 2-plane in RD, 1. Okay, this 2-plane is like an R1, 1 because it has time in it, because it has the rest momentum of the massive particle. Okay, orthogonal complement to this R1, 1 and RD, 1 is an RD-1. And rotations in this orthogonal complement are SOD-1. Okay, so this kinematics is important to keep track of. There is a distinguished 2-plane in 3 particle scattering. This is R1, 1, and there is an orthogonal RD-1, D-1, which is rotated by SOD-1. Now, what can we say about the polarizations of the gravitons? The part of the polarization of the gravitons that lies in the R1, 1. First, the gravitons can have absolutely any polarizations in the orthogonal part. Okay, so for instance, we look at the graviton 1, the polarization 1 orthogonal is the part that is orthogonal to this 2-plane. And that is completely unconstrained. It's completely unconstrained because the constraints on graviton polarizations are orthogonality with their own momenta. And then there's some gauge invariance shift, but also that's gauge invariance with their own momentum. So everything that's orthogonal to the momentum plane is completely unconstrained. So the gravitational polarization has an orthogonal component and a part in the scattering plane. The orthogonal part is completely unconstrained. Now, most general graviton scattering amplitude will be epsilon1 perpendicular, which is unconstrained, plus A1, K1 plus A2, K2. Because that's the most general parametrization of something in the A1, K1 plus A2, K2 is the most general vector in the scattering plane. However, now we have the condition that K1 dot epsilon 1 is 0. K1 dot epsilon 1 perpendicular is 0 by definition, because epsilon 1 perpendicular is orthogonal to the whole scattering 2-plane, and therefore orthogonal in particular to K1. Also, K1 dot K1 is 0, because our gravitational particle was massless. But K1 dot K2 is not 0 in general. And so this equation that epsilon 1 dot K1 is equal to 0 sets A2 to 0, tells us that the component of epsilon 1 in the K2 direction must be 0. in this decomposition. That's the perpendicular A1, K1 and nothing else. Now this A1, K1 part is exactly the part that can be shifted away by pure gauge. So the scattering amplitude, while epsilon 1 has this orthogonal part and an A1 piece, the scattering amplitude cannot depend on A1. So the data in scattering is just this epsilon 1 perpendicular. Okay? So there's the polarization dependence of gravitational scattering. Same would be true for photon scattering. Gravitational scattering, the answer depends only on the part of the polarization that lies in the orthogonal d minus 1. I was working in R d comma 1. Okay. I hope that was not confusing. Okay. Okay. And sorry. In my words, I was working in R d comma 1. Sorry, but in my transparencies, I've been working in R d minus 1 comma 1. So let me just say that one more time, just to match with the transparencies. We're working in R d minus 1 comma 1. The orthogonal plane is an R d minus 2, and the scattering plane is an R11, and the orthogonal plane is left invariant by rotations of SOD minus 2. Sorry for that confusion. Okay, great. So for the gravitons, we've got these two epsilon perpendiculars that are symmetric traceless tensors in SOD minus 2. Fine. Now what about the particle? The particle, the massive particle that you're scattering into, is classified by some representation of its little group, and its little group is SOD minus 1 because it's a massive particle. So it's classified by some representation of SOD minus 1. Now, SOD minus 1 is the SOD minus 1 that is orthogonal to K1 plus K2. Where K1 and K2 are the momentum of the two gravitons, K1 plus K2 is proportional to the momentum of this massive particle. And the SOD minus 1 is the SOD minus 1 orthogonal to the momentum of this massive particle. So SOD minus 1 is a part of, is a part of rotational group that is orthogonal to K1 plus K2. Okay, K1 plus K2 is part of the scattering 2 plane, but there's another vector in the scattering 2 plane, K1 minus K2. So if I wanted to understand what the representation content of this massive particle was in the SOD minus 2 that leaves the scattering 2 plane unchanged, that leaves it invariant, then what I have to do is to take the particular representation of SOD minus 1 that our massive particle lives in and check what representations of SOD minus 2 this descends into. I think these are called branching rules in group theory. Take a representation of a higher group and find what representations of a subgroup you get from a particular representation of a higher group. Okay, now this is simple group theory and it's easy to do. Finally, the final 3-point function is the most general SOD minus 2 invariant that can be built out of the traceless symmetric tensor of one traceless symmetric tensor of SOD minus 2, that's the first graviton, the second traceless symmetric tensor of SOD minus 2, the second graviton, and then our massive particle, which was in one representation of SOD minus 1, and therefore in several representations of SOD minus 2. Okay, so all you have to do is to decompose the SOD minus 1 representation into SOD minus 2 representations, make all the SOD minus 2 invariants you can out of these two symmetric tensors, and this what you get from descent. And then there's one more thing you have to do. You have to impose Bose symmetry because the two gravitons were identical. So you do the Clebsch-Gordon coupling of the gravitons so that you only keep the symmetric part. Okay, so I've written that here. What we have to do is enumerate all SOD minus 2 singlets in the product of two SOD minus 2 traceless symmetric tensors and one copy of any of the SOD minus 2 representations that descend from R, and retain only those singlets that respect Bose symmetry. Now you see that this is not a hard exercise, and it's not hard therefore to enumerate all graviton-graviton massive particle three particle couplings, and it's also not hard to write down the Lagrangians from which they follow. Okay, and we've done this exercise and we produced a table enumerating the set of all representations in which the massive particle can be so that it can scatter with two gravitons, and also explicitly enumerating both the S matrix, the 3-particle S matrix, as well as the Lagrangian from which it follows. Now, I'm just showing you these tables to show you that that we have some answers. Okay, there's some shading in yellow which denotes contraction with K1 minus K2. None of the details matter. Okay, I mean they matter, but I'm not going to try to ask you to pay attention to any of the details. The main point, there are 2 or 3 main points that you have to take away. A, we have a complete classification of these graviton, any particle scattering amplitudes. B, one qualitative feature that comes out of this this answer is the following. Just by explicitly looking through our list, just by looking at our list, we see that every such coupling, every coupling of GG particle is always 4 derivative or higher. Okay? Why is this observation important? Well, it will be important technically at the last part of my talk. But already it's important qualitatively at this point, because it makes precise a statement I'd claimed in my first lecture. I claimed that in any 2-derivative theory of gravity, interacting with any other fields, you never have tree-level scattering of 2 gravitons to some other particle. This gives a proof of that fact, because all couplings of gravity, 2 gravitons to any other particle, is at least 4 derivative or higher. And we show this just by simple group theoretic enumeration. Okay? Now you might wonder why this was true. Why was it true that every coupling of 2 gravitons with any other particle is 4 derivative or higher? And the physical reason for this is the following. Genuine couplings of 2 gravitons with anything else is always through the Riemann tensor. Okay? This is not obvious, because you might have thought that, okay, if I've got a square root, let's say I just take square root G and I expand it. This has all powers in the gravitational coupling. So even a term with square root G and let's say del phi, the whole thing square, has, or something else, has many powers of the graviton. See, it's not obvious that powers of the graviton always have to come through Riemann tensor. But the point is, for the purpose of scattering, that they do. You know, all other terms that have 2 H's with anything else also have 1 H with anything else. And when you do the field redefinition that gets rid of this 1 H with anything else term, the diagonalizing the propagator, you also get rid of the 2 H with anything else term. This is a sophisticated version of what we saw with going to Einstein frame. Okay, so at this point, this is all I want to say about the pole contributions. By classifying 2 graviton to particle contribution couplings, and by knowing, because we've known since we were undergraduates, what particles can run, we've effectively classified all pole contributions. However,
Hello?
Yes.
Yeah, Shiraz, sorry, there's a question in the chat. So the question is, does this method automatically implement the Schouten identities?
Oh my God, I have no clue. What is the Schouten identity? It implements everything it should implement, but I don't even know what the Schouten identity is. If somebody can tell me what Schouten identity is, maybe I will know.
So yeah, there are these relations between the contractions of Riemann tensor, for example, RABCD, RABCD. The same is related up to a factor of 2 to RACBD, RABCD.
Perfect. Yes, this will automatically implement that because it's purely on shell. It's not even talking about Riemann tensors. You see, this is just some group theory talking about coupling of kinematical data. So when maybe the question was that in addition to giving the S matrices, we also produced Lagrangians. Well, we produced one Lagrangian that would give rise to this coupling, and by using your Schouten identity, you maybe produce a different looking Lagrangian that gives rise to the coupling.
Right.
But that's, yeah. Okay, any other questions? Okay, excellent. So before we move on to the part that's more difficult, namely the classification of the polynomial.
Sachin has a question. One second. Sachin has a question.
Yes, Shiraz, just to understand, you have been doing this classification based on covariant notation, right? And trying to fix whatever you can get, and you're using some gauge fixing, etc. If I do the classification, let's say in particular light cone variables, or I try to do it try to write down the amplitude in spin helicity variable.
Right.
Do you get the same number of things?
Yes.
Sorry, because for massless particles, at least it is known that if you do covariantly, if you do light cone variable or spin helicity variables, there is a mismatch between the number of independent structures that is available.
Well, this classification here was just done by group theory.
Okay.
So this really does not use any formalism. Now you may be asking about the Lagrangians, actually. Maybe that's your question.
Yeah.
Well, I also think that Lagrangians, there's a one-to-one correspondence between S matrices and Lagrangians modulo total directives and modulo field redefinitions. And Lagrangian terms also, Lagrangian is a Lagrangian, right? I mean, I don't even need to specify gauge. You can work gauge invariantly for that. Maybe I'm not understanding your question. Can you, there's a mismatch between what and what again?
Said maybe I can talk to you later, but let me just say my question. So suppose you try to write down, let's say, spin S, spin 0, or some kind of a 3-point amplitude. Yeah. Covariantly, let's say the gauge that you are choosing, epsilon dot k is 0. That kind of you write down the amplitude. You can count the number of structures. Right. Then you say you choose to write down how many are possible in spin helicity variable, let's say. Okay. Or in light cone variables. Yes. You will see that there actually is a mismatch, and that mismatch, for example, there is a mismatch that you can show. That has been known in the literature, that there is a mismatch. And I was just wondering if you.
No, but I don't understand this mismatch. For instance, one of the things we've checked is that when we go to 4 dimensions, where spin helicity variables work well, we get the same answers that everyone else gets. You see, in 4 dimensions, very easy, because there's effectively, we get the same answers that the spinner helicity people say. For the number of, let's say, photon scattering amplitudes.
Right. Let's say I have photon graviton scattering amplitude.
You want to do two-part, all 3 massless. Okay, go on. Yeah.
In that case, actually, you can count and show that there is a mismatch.
Maybe this has to do. What about doing to start with photon something massive? Is there also a mismatch there?
For massive things, I am not sure yet. I have to look up. But for massless, I know there is a mismatch for sure.
Okay. Yeah. This calculation here was for 2 particle, 2 massless and 1 massive.
1 massive particle.
And I don't think, it's just a completely invariant thing, right?
Okay.
We do it by group theory. It really doesn't depend on formalism.
Okay.
Right. And we can also produce a Lagrangian for each of these structures. Okay. Now it could be that when you do the 3rd guy massless, but physically, how can it be there's a mismatch? I mean, what about if you write down Lagrangian? Maybe we can discuss this later.
Yeah. We will discuss it. Okay. Thank you.
Yeah. Okay, fine. It sounds to me that there has to be a correct answer, right? You write one of these terms, there will be as many Lagrangians as do it or not. Okay, maybe you can tell me about it. Yeah. Anyway, in what we're doing, we see no subtleties of this. Okay. Fine. Okay. So, great. So now that we have these 2 gravitons to one massive particle scattering amplitudes completely classified, I said that in principle this completely determines this pole kind of contribution, right? And that's true in principle, but what about in practice? Can one actually write down explicit formulas for the pole contribution? Well, for scalars, the answer is yes. It's easy. It's possible, and it's easy to do. For gravitons and gauge bosons, as far as I'm aware, nobody's done this in above 4 dimensions. In fact, this is an exercise that I'm undertaking with an undergraduate student, Shoaib, and my PhD student, Shuman, at the moment. It's not a difficult exercise, but just to complete this kinematic classification. Luckily, we did for our final answers, we didn't need this explicit form. We just needed some features of it, which we could deduce. But let me give you 2 minutes on this, on how this goes. I'm giving you this large at least partly because it's going to make contact. It makes contact with what you've already been hearing about in Simon Caron-Ho's lectures. Okay, see, what's going on here? What's going on here is that this two-particle to massive particle scattering amplitude is effectively the overlap between a massive particle and a two-particle graviton state. Now, a massive particle in its rest frame transforms in a particular, it transforms in some particular angular momentum state. So this two-particle to massive particle scattering amplitude is actually the same thing as asking what are the projections of the two-particle graviton state to a state of definite angular momentum. Okay, so this classification we've done here can be thought of as giving the component, as projecting out the components of the two-particle graviton state into bases with definite into components with definite angular momentum. Okay, now what we did here was to look at definite angular momentum, including definite m components of angular momentum. So angular momentum is labeled by a representation which would be L for SO3, and vectors within that representation which would be m for SO3. Okay, so the two particle to massive particle scattering amplitude we presented was for scattering into a particular polarization, so particular of the massive particle, and so a particular m state of the massive particle. However, when we look at this block, two gravitons scattering through a massive particle to two other gravitons, when we look at such a block, that scattering happens through all possible polarizations of the massive particle state. So when you think it through, you see what this block amounts to is simply the following. You take the two-particle state, take the part of that two-particle graviton state that transforms in a particular angular momentum, and take the part of the other two-particle state that transforms in the same angular momentum, and then fuse the two. So just look at the projector of the part of this two-particle angular momentum in a particular two-particle state in a particular angular momentum. Look at the part of this two-particle state in the same angular momentum, and then take the dot product of those two parts. Okay, so that's what this block amounts to, is effectively projecting your particle states into states of definite angular momentum. Okay, and wording it this way, it's easy to use group theory, in particular the theory of, it's not hard to use group theory, in particular the theory of spherical harmonics, to determine the explicit form of all these scattering amplitudes, including their polarization dependence. And we're in the process of getting everything straight for this, and the end result will be some big table for all possible scattering amplitudes. Okay, now I told you that this made contact with what Simon Caron-Ho told you about, and though I haven't had the chance to attend all his lectures, a lot of what he was doing was just about contact scattering through some contact term. So what did I mean by saying this analysis, which seems to care about intermediate particles and so on, has to do with what he's telling you about? Well, the point is this, that once you think of scattering in this way, that I will take the two-particle state here and project onto a state of definite angular momentum. The two-particle state here and project onto a state of definite angular momentum and scatter and then overlap, then it doesn't really matter what is in the middle, whether it's a particle or a contact term in the middle. So, this basis of looking at scattering amplitudes, taking scattering amplitudes and decomposing it into the two-particle states having definite angular momentum, is a standard technique in the study of scattering amplitudes, mainly so far employed for scalars, but the idea goes through for every particle. It's called the partial wave decomposition. And the partial wave decomposition, as you've probably heard of in Simon's lectures, is very convenient because you see, while if I just, because angular momentum is conserved in scattering. That's why if you take an angular momentum in your initial state and angular momentum in your final state, you only have to glue the same angular momentum together. Moreover, the number of two particle states with any fixed angular momentum is always finite. Okay, and so S matrices in this basis become a finite dimensional matrix rather than an infinite dimensional matrix in this partial wave basis. And therefore, the constraints, for instance, of unitarity are very easily implemented in this partial wave basis. Okay, so these blocks involving exchange of particles here are nice to understand what happens, what the structure of your S matrix is when you have an intermediate particle going through. You get Gegenbauers for scalars and generalizations for higher particles. It's nice to understand for these intermediate massive particles, and that was the use we put them to. However, the same basis is a general group theoretic tool that is useful for analyzing, for instance, unitarity and dispersion relations in scattering amplitude. So it's useful to have a complete classification of S matrices in this basis. This is a kinematical exercise we are undertaking now. Not that it impacts the rest of the lectures, so we can forget about it. And we can forget about it for purpose of the rest of the lectures. Okay, any questions or comments? That ends my discussion of the poll contributions. Any questions or comments on this part?
Hello, so yeah. Shiraz, so
yes.
This kind of classification, has it been done for like gluons or photons?
Photons, as far as I know, no, not above 4 dimensions.
Okay.
So in fact, in what we are doing, we're first working on the photon case, and gluons would be similar, and then working out the graviton case. So photons are easier, test case. Though of course sometimes you're ignorant, so it could be that there is some part of the literature where in some specific dimension somebody's done it, but I've only seen the 4 dimension.
Okay. Yeah, I don't see any further questions.
Further questions? Perfect. Okay, so this way of thinking of it completely classifies all pole exchanges and actually does more, right? It gives you basically a partial wave basis for scattering amplitudes. But for what we're going to be talking about, we've got completely classified pole exchange. Okay, so every pole exchange corresponds to a good physical particle. It's characterized by a mass, and then by the 3-point couplings that appear here and here. And the 3-point couplings always have only a finite number of options. Okay, so we've got pole contributions under control. Fine. Now we're looking at classical scattering amplitudes. Okay, and classical scattering amplitudes, apart from this pole contribution, have these contact terms. Okay, polynomials. So now the remaining job here is to classify all polynomials in S matrices. Okay, now what do we need to do that? Well, we want to classify all polynomials that are polynomials in Moyenta that are A, Lorentz invariant, which means all indices contractor. B, separately quadratic in all polarizations, because we're looking at gravitons. C, gauge invariant. And D, both symmetric. Much of the fun that happens in this classification program happens due to the interplay of the gauge invariance condition and the Bose symmetric condition, as we will see. Okay. Now let me repeat these conditions here slightly more mathematically. Lorentz invariant means contract structures. Separately quadratic in each epsilon I means separately quadratic in each epsilon I. But look, remember that these epsilon i's obey pi dot epsilon I is equal to 0 and epsilon I dot epsilon I is equal to 0. Okay. Invariant under gauge invariance means invariant under the shift, as we've seen. And Bose symmetric, of course, means permutation invariant under the permutation of the four gravitons. Moreover, as we've emphasized before, S matrices are to be regarded as evaluated on shell. Okay, so these polynomials are only to be evaluated when these equations of motion are obeyed. That is, pi squared is equal to 0, pi dot epsilon I is equal to 0, and epsilon dot epsilon is equal to 0. Two S matrices that differ by, let's say, a pi squared times something are to be regarded as the same. Okay, so the question is, how do we classify all these polynomials? And when you're trying to classify something, one way of making sure you know what you've got control of what you're doing is, can you count them? Of course, counting will give you infinity if you just count everything, because there's a way. But you can count graded by derivatives. So that's a clear counting problem. It's a sharp measure of whether you know what you're doing. Okay, so we want to start trying to classify these S matrices. Okay, so to begin with, let us put aside the requirement of S4 invariance. A lot of the fun will come from this, but for the first, start with, let's put that requirement aside. Okay, so imagine that M is any polynomial S matrix that obeys conditions 1 to 3, but not 4. So it's in an unsymmetrized polynomial S matrix. Okay. Now, if M is such an S matrix, then it's obvious that P of S, comma T times M is also such an S matrix. That's because these conditions 1, 2, and 3, one is the Lorentz invariance, but S and T are Lorentz invariance objects. Separately quadratic in epsilons and conditions in epsilons, but S and T don't depend on epsilon. And invariant under some shifts of polarizations, but S and T don't depend on epsilon. So these three conditions that tell you when a class S matrix is a good one, if it's obeyed for some M, it will clearly be obeyed for functions of S and T times M. I'm saying S and T rather than S, T, and U because U is dependent on S and T. Okay. Now, whenever you have the structure that if you've got a good object, you can act with polynomials of some other some polynomials of something and also get a good object. This has a name in mathematics. This structure has a name in mathematics. The name is that you've got a module. Okay. One place where many of you have encountered modules are Verma modules of the Virasoro algebra. Okay. We'll go back to that analogy many times. So at least these unsymmetrized S matrices are modules. Now, just one or two sort of definitions. All of us as physicists are very familiar with vector spaces. Okay. Vector spaces are spaces that can be, where you can multiply vectors by something and then add and subtract. Okay. The something that we usually allow ourselves to multiply with for vector spaces are real or complex numbers. Okay. Real or complex numbers are examples of a field. Okay. Where, and a property of a field is that every non-trivial element in the field has an inverse. Okay. Basically, you can take field elements and divide with, because these are just, for instance, in our mind, for the common examples, they're real or complex numbers. A module is a very similar structure where you can multiply by something and take linear combinations. But the one thing that you cannot do is divide by those things that you multiply by. That is, the module is defined, not the things that you allow to as coefficients of linear combinations are not elements of a field. Elements don't have inverses. Okay, they're elements of what mathematicians like to call a ring. Okay, a ring is a structure where you can perform all the operations that you can perform in a field except division by field elements. Okay, what is the importance of that? The importance of that is as follows. If suppose you've got an element M and another element P, S and T times M. Okay, while you can go from M to this element by multiplying by these polynomials, you can't go back from this element to M by multiplying by polynomials, because division is not allowed. Okay, so there's a sort of one-way kind of structure in a module. What you should keep in mind again is the Verma modules. That also has a one-way structure. States are built on top of primaries. From a primary, you can go by, you can act with raising operators to get any other state, but you can't act with raising operators on any other state to get back a primary. Okay, fine. Now consider two module elements A and B and a non-trivial ring element R. If B is equal to R times A, we say B is a descendant of A. Again, think of Verma modules. Other states are descendants of the primaries because you can act with raising operators to go up. Okay. A module element that is not the descendant of any other module element is said to be the generator of the module. Generators like the primary states of a Verma. Okay. The generators, and I've written here, think Virasoro primaries of a module, play the same role that basis elements play for a vector space. Because you can get to every element of the module by multiplying more and more ring elements. In this case, just polynomials of S, T, and U, acting on these generator states. Finally, last two abstract definitions, then we go and explain how this plays into it. Suppose I have a subset G of the made up of some elements of the module, okay, and this G, a subset G of the module M is said to generate M if the smallest submodule which contains G is M itself. Okay, so in other words, if you've got a bunch of elements and all the states that you can get as descendants of these elements is the full module, okay, then these elements whose descendants give you the full module are the generators. It's very much like the set of primary states in a full Hilbert space that has Virasoro symmetry. Starting from these primaries and then acting with the Virasoro generators, you get the whole Hilbert space. Okay. Finally, a module is said to be finitely generated if it has a finite number of generators, finite number of primary fields, let's say, finite number of Virasoro primaries. Okay. Oh, so there's one more abstract thing, I'm sorry. Okay. Three more abstract things, sorry. A generator set G is said to generate M freely if the following condition holds. If there is no non-trivial relationship between descendants of all the generators of G. Okay? In the case, okay, that a set of generators G generates this module freely, every module element has a unique decomposition in terms of descendants of the generators. Okay? On the other hand, if a condition like this holds, then you give me one decomposition of an element in terms of descendants of generators, I can add to it this condition, this expression. That's also an expression for that element in terms of generators of the module, but it's a different one. Okay, so a bunch of generators generates a module freely if there is a unique way of taking descendants of these generators and getting every state in the module. Now, this does not, when this happens, when there exists a set of generators that generates a module freely, the module is said to be a free module. Okay, a free module is a very simple structure because it's completely characterized by its generators and this ring, the set of everything you can build on top of it. Okay, now this does not always happen. All modules are not free. In terms of Virasoro generators, this is like having null states. You can sometimes get descendants of some primary that gives you 0. Okay, so that you've got some non-trivial relation between descendants of a primary. Okay, and so adding that relation to one expression for a state gives you the same state. Okay, so non-freeness is like having null states. Okay, great. When the module is not free, by definition, it has a collection of non-trivial relations, which are descendants of these generators that add up to 0. Now, if you've got a descendant like this that adds up to 0, clearly any R on top of this descendant also is 0 because it's a descendant, it's some polynomial acting on 0. And thus, the set of all relations themselves form a module because there are generators and primary states of the relations. Okay, and a general module can be thought of as generators, and it has generators. Then these generators have their null states. These null states have their own null modules, and then there may be null modules of null modules, and so on. The general structure of a null state of a module is enumerated by giving you the generators and all its null states, and keep going, and can in general be quite complicated. Luckily, in our case, we will have only very simple modules appear. Okay, so this is all I wanted to say about these modules. I'm going to use this language, and I'm sorry for it, but it's sort of efficient language and useful. Maybe I could pause briefly to ask if there are questions or comments about this before we proceed. Okay. I'm going to assume, yes. Was there a question?
No, I don't see any question.
Okay. I hope this doesn't mean that it just was too fast. Okay, the basic point was just that if you've got an S matrix that is, without symmetrizing for now, you've got an S matrix that obeys all the good properties, then polynomials of ST on it also obey all the good properties. And so there's a one-way relationship. Given one good S matrix, I can build an infinite number more by acting with polynomials of ST and U. Sometimes you take two good S matrices and act on them, you get the same thing. It doesn't always go one-to-one. Okay, that's these null states. Okay, anyway, fine.
Actually, Shiraz, I had a question.
Please.
So this analogy with Verma module,
yes.
Is it actually, precisely true in the sense that if I have in an ADS-CFT context, like the thing that we were talking about last time, there's some Verma module classification on the CFT side, which kind of maps to this tensor structure classification for the S matrices.
Interesting. You see, these CFT Verma modules are effectively classifying interactions. So it's sort of like a classification of 4-point functions of the CFT. Okay. Whereas the connection you're drawing would naturally be in sort of descendants of states on the CFT. So I think not. Unless there is some way of thinking of it that makes it true, I think not. It's more sort of a Verma module type classification of particular kinds of CFT 4-point functions, namely those kinds that are generated from local interactions in the bulk. If we didn't have this locality property, then we wouldn't have this module structure. Because an S matrix without locality will allow you to also to divide by S. And then this whole structure goes away. Okay, so I think it has to do with classification of certain kinds of 4-point functions of CFTs, which not the usual Verma module structure of states, as far as I can see.
Okay, so it's classification of some kind of contact terms in these 4-point functions, is that?
Not exactly contact terms. You see, because contact terms in the bulk don't lead to contact terms on the boundary.
Yeah, I mean the boundary contact terms.
Boundary contact. No, yeah. What it is classification of the bulk contact terms. Right?
Okay.
Right, because we're doing this the S matrix classification, which is bulk contact terms. So I don't think it's boundary contact terms. In fact, I would say it's probably the classification of bulk point singularity. Well, that's an interesting point. If you look at all classical S matrices that come out of ADS-CFT, so S matrices generated by Witten diagrams, nobody's ever proved this, but I think it's probably true, that the general analytic properties of these S matrices plus the structure of their bulk point singularity completely determines the S matrix. It completely determines the correlator, the boundary correlator. So, there's a way of taking this class of correlation functions, 4-point correlation functions, and parametrizing them by their bulk point singularity. This is a fancy way of saying that they're parametrized by whatever interaction created them in the bulk. Okay, but it's a way of making sort of the classification sort of invariant, just directly in terms of boundary correlator structures, and it would be some module structure for all such things. I think. I hope I've not missed something in the answer.
So this is the analog of this Hemsky, Wojcinski.
Exactly.
Yeah,
exactly. It's exactly that kind of classification. Exactly.
Okay.
Exactly.
Okay, thanks.
Okay. Okay, great. So far I've discussed these permutation unsymmetrized S matrices. But of course, S matrices have to be symmetrized. You have to put the constraint of invariance under S4. However, part of that invariance Okay, now one thing you can show is the following, that S4 mod Z2 times Z2 is S3. And in fact, Z2 times Z2 is a normal subgroup of S4, so it doesn't matter whether you mod it out from the left or the right. This is a very robust relation. If it was a less nice subgroup, I would have to tell you more about what this modding means, but for this subgroup, I don't. However you do it, you'll get the same answer. Okay, so S4 mod Z2 times Z2 is S3. Now, what is this Z2 times Z2? S4 is a group of permutations. And consider that Z2 times Z2, that is the subgroup that is given by identity and simultaneous permutations of two pairs. So, for instance, suppose you take the pairs 1 and 2, and I permute, and also permute 3 and 4. That's one Z2 times Z2 element. Or I could take 1 and 3 and permute, and also permute 2 and 4. Or I could take 1 and 4 and also permute 2 and 3. So you see there are three such elements of simultaneous permutations. That together with identity makes a four-dimensional, gives you 4 elements, and you can easily convince yourselves that these 4 elements form a subgroup of the permutation group, and in fact the subgroup is Z2 times Z2. Okay? Now, I missed a slide, sorry. So this is what I've said here. This, where am I? Okay, yeah. So it's not difficult to verify that this subgroup of the, permutation group, the Z2 times Z2 subgroup of the permutation group is special for scattering for the following reason. This subgroup leaves the variables S, T, and U unchanged, invariant. Let's check that for a particular example. Let's take the element of one non-trivial element of Z2 times Z2, which is permutation of 1 and 2 and permutation of 3 and 4. So let's look at the variable S. S is P1 plus P2 the whole thing squared. But if I interchange 1 and 2, of course, it doesn't change. Now look at T. T is P1 plus P3 the whole thing squared. Okay. So I'm supposed to interchange 1 and 2. So 1 goes to 2. But I'm also supposed to interchange 3 and 4. So 3 goes to 4. So this is P2 plus P4 the whole thing squared, which is the same as T by momentum conservation. Similarly for you. Okay. So all three, S, T, and U, are left invariant under Z2 times Z2 permutations. So now, instead of being so crude as to look at only at S matrices that have no Bose symmetry at all, suppose we look at those S matrices that have that are invariant under a small subgroup of the permutations, namely invariant under Z2 times Z2. Okay. I'm going to give these a name. I'm going to call these quasi invariant S matrices. I call them quasi invariant because they're not completely permutation invariant, but they're not completely permutation uninvariant either, because they're invariant under Z2 times Z2. Okay. Now the fact.
Shiraz?
Yes.
There's a question whether this Z2 times Z2 is neither Bose nor crossing.
Z2 times Z2 is neither Bose nor crossing. Yes, it's not crossing because crossing changes ST and U. Okay, and it's not all of Bose, but it's a part of Bose symmetry. Bose symmetry is invariance under the full permutation group. This is invariance under some small subgroup of it. So it's a part of it, but not the full thing. Okay. The importance of the Z2 times Z2 is precisely that it's not crossing. I mean, precisely that it does not act on ST and U. Okay. Now, because it does not act on ST and U, everything I said about module structures goes through unchanged for quasi-invariant S matrices. These S matrices that are not invariant under all of Bose symmetry, but only under Z2 times Z2. They also form a module. Because since ST and U are invariant under the Z2 times Z2, if I have a good S matrix, I multiply by polynomial of ST and U, it doesn't change anything. Okay, so everything that I said that was true for these unsymmetrized S matrices also holds for these quasi-invariant S matrices. Okay, now quasi-invariant S matrices are in general not fully permutation invariant, which tells us that they transform in representations of the part of the of S4 that has not yet been implemented. But the part of S4 that has not yet been implemented as invariance is S3. So these quasi-invariant S matrices transform as a representation of S3. and so can be decomposed into irreducible representations of S3. Okay? Now, S3 is the permutation group of 3 objects. In fact, in the current context, this S3, the remaining S3 acts on ST and U by permuting ST and U. Okay. Now, so the idea is this. The way we're going to proceed is this. We're going to work with these quasi-invariant S matrices, which have this nice module structure. After completely understanding this, the module structure, which is very convenient for various bits of analysis, at the final step, what we will do is to take the part of this module, and the whole module can be decomposed in representations of S3. S3 has 3 irreducible representations. The completely symmetric representation, which I call S, the completely antisymmetric representation, which I call A, and a mixed representation, which I call M. S and A are one-dimensional representations. M is a 2-dimensional representation. And just to say that the defining representation of S3 that acts on 3 objects is not irreducible. It reduces into the sum of an S and an M. We will sometimes call the combination of an S and an M, this defining representation, we'll sometimes call it this bold-face 3. Okay, so coming back, we've got this module of quasi-invariant matrices that are invariant under Z2 times Z2, and they can be decomposed in representations of S3. So we're going to perform much of our analysis with this unnecessarily unphysical structure that imposes constraint only on S3 times S3. And right at the final step, we will project our final answer into that part of the module that transforms in the S, that part of the module that is invariant under S3. And that will give us the set of all physical S matrices. Working with this one step back, with this larger mathematical structure is convenient, even though in the end, we only want the projection onto S3 signals. Okay, so that's what I've explained.
So there's some question.
Yes.
So whether in the Bose symmetry, you exchange only the final or the initial particles?
In the Bose symmetry, we exchange only final or initial particles. Okay. But you see, consider a Lagrangian term. This Lagrangian term is invariant under exchange of all 4 H fields. You see, this in a way is to say that when you add crossing invariance with this Bose symmetry, it's invariance under all 4 S fields. And this is most clearly seen when you look at it in terms of Lagrangians. The 4 H's that go into this Lagrangians are the same. Okay, so the final S matrix has to have this full permutation invariance, part of which is crossing invariance, because it doesn't leave ST and U unchanged. Is this clear?
Yeah.
Okay.
See.
Okay. So, but precisely because the remaining part of this permutation invariance also acts on ST and U. Precisely because of that, we're dealing with the S3 separately. Okay. Now, right. So I want to understand a little bit more now the structure of these modules. Okay. The first thing I'm going to do as a little exercise, I'm going to ask the following question. Suppose I have the set of all polynomials of ST and U. Okay, I have the set of all polynomials of ST and U, every polynomial I can make. And I want to decompose the space of polynomials into representations of S3. Okay, and then I ask, how many such representations occur at any derivative order? Okay, so what's derivative? ST and U are each taken to have derivative order 2 because they're mass to the power 2. Okay, so another way of saying it is the following. The set of all polynomials of ST and U, can be counted by weighting polynomials with their derivative order. So with their derivative order as follows. If I have a polynomial which is degree n in ST and U, I will weight it by x to the power 2n. Okay? And we can compute a partition function over the set of all polynomials of ST and U. This is not a difficult thing to do at all. A slightly more involved an interesting calculation is to not compute that partition function once and for all, but separately calculate a partition function over all those polynomials that are in the S representation, all those polynomials that are in the A representation, and all those polynomials that are in the M representation of S3. Okay, this is not it's not a very hard exercise. And when you do that, you get the following answers. The polynomials in the S representation have this partition function. In the A representation, have this partition function, x to the 6 times d, and M representation, this partition function. I'm not sure exactly, but Schumann might lead you through some of these calculations in the tutorial session. Let's give a quick interpretation of this ZS. We want all polynomials of ST and U that are invariant under S3. But I told you that S3 acted on ST and U just by permuting the three. Okay? Now, you can ask, can you find simple monomials of ST and U that are invariant under permutation? And there are two very simple monomials, S square plus T square plus U square and STU. Okay? S square plus T square plus U square has dimension 4. So that's, and you can make any number of powers of this. So that's 1 minus x to the 4. And then the STU has dimension 6. So that's this 1 minus x to the 6. So another way of saying it is that the set of all polynomials that are in the singlet representation are simply polynomials of S square plus T square plus U square and STU. Unconstrained polynomials of those guys. And all of the set, the polynomial partition functions in other representations also have a factor of D, which comes from the fact that if you've got a polynomial that's in some particular representation, then you multiply it by another polynomial that's in the singlet, it stays in its representation. Okay, so these partition functions have very simple structure and take this form. Okay, so you can decompose the space of all polynomials of ST and U into their S3 components. Okay. Now, this decomposition has also given us the decomposition of a module of just, one free module by itself, whose primary lies in the S representation. Because if you've got a primary in the S representation, then you build all, you put descendants on this, and you get these many states in the S representation, these many states in the A representation, these many states in the M representation. If we're only interested in the projection of this part to singlets, we just get this part. Okay, right. Now, what about the Verma module of a generator in the A or the M representation? Well, one way of understanding that is the following. You have what you get from polynomials tensored with what you got from the generator. Now, it's easy to work out the following group theory rules. The Clebsch-Gordon rules for S3 go like this. Anything with S is that thing. A with A is S. A with S is S. All these are sort of obvious things. You'll guess them in a minute. A with M is M. This maybe is a little less obvious. And the most non-trivial one is M with M is S plus A plus M. For current purposes, all I want you to look at is the following. You only get an S on the right-hand side of one of these relations, okay, if the two representations are the same. This is very similar to SU2. You only get a singlet in SU2 if you fuse J with J. You never get a singlet when you fuse J1 with J2 and J1 is not equal. Okay? And so this tells you that if you're going to fuse two representations and then pick out the singlet, you're only getting them when these two representations are the same. So suppose we take the Verma module of a primary that's in some representation, and then you fuse with this set of the representation of all the representations you get from polynomials. Let's say we took a Verma module where the generator was in the M representation, and then we fused with the content of the state space of polynomials of ST and U. The final singlets we will get are only from this part. And so this quantity gives you the restriction to singlets of the Verma module built on top of an M representation, a primary in the M representation. Okay, so these quantities can also be thought of, now you see, as the partition function of a module in the S, A, or M representation restricted to singlets. Okay, So now we have very good control over these modules. If you have a primary in some particular irreducible representation of S3, and it's just a pure Verma module with no null states, we completely know how to count these, to count the states. Okay. Now with the Verma modules under control, all that remains is to characterize the generators of these modules and their null states. Okay. Okay, yes. Fine. Let's move. Let's keep going. Okay. The classification of these generators and their null states is an interesting problem and is given clean mathematical implementation by a certain maneuver. Okay. The main difficulty in this whole problem goes as follows. There's the interplay between this Bose symmetry and gauge invariance. Actually, between three things: Bose symmetry, gauge invariance, and locality. The interplay between these three structures makes this problem a little non-trivial. Okay, I'm going to very quickly, maybe in the next 5 or 10 minutes, explain to you roughly how we proceed to solve this. See, when we were studying the scattering of 3 particle scattering, 2 particles going to a third particle. Okay, in that problem, I described to you this special kinematic construction, namely the scattering 2 plane, which is the 2 plane that was built out of, that was linear combinations of the 2 scattering vectors. When we're scattering four particles, in a similar way, there's a scattering 3 plane. Okay, because there are 4 scattering momenta, but one of them is dependent on the others because of momentum conservation. Okay. Now, in order to implement gauge invariance, it's useful to keep track of the scattering 3 plane for precisely the same reason it was for 2 particle scattering, because gauge invariance always mixes up things only inside the scattering 3 plane. The part that's orthogonal to it is completely independent. Okay, so every polarization vector can be decomposed into an orthogonal part, orthogonal now to the scattering 3 plane, and a part in the scattering 2 plane. Okay. Epsilon I perpendicular is completely free data. Okay. Epsilon parallel is not completely free because it obeys one condition, namely it's orthogonal to its own momentum. That constrains epsilon I parallel. And B, there is one redundancy, namely shifts by its own momentum give you the same answer. Okay. So effectively, there's one piece of data in epsilon I parallel. Okay. There's one piece of data in epsilon I parallel. Okay. And that one piece of data by a choice of, that one piece of data can be parametrized as follows. Okay. That one piece of data can be parametrized by these quantities alpha that chooses out particular combinations of vectors in the scattering 3 plane that automatically obey the condition that P1 dot this vector is 0. And then, of course, you can add anything times P1 to it. Okay? So from this point of view, AI is a pure gauge, alpha is physical, and epsilon 1 perpendicular is physical. Okay? The fact that our polarizations were traceless was one constraint between epsilon I, the dot product of the epsilon I perpendiculars and these alphas. Okay. So if we treat, that tells you that the dot product of these epsilon i's are completely determined in terms of alpha i's. And so up to polynomials in alpha I squares, epsilon I dot epsilon I perpendicular can be just treated as 0. Okay, so the data really is in these traceless epsilon I perpendiculars and alphas for each of these for each of these gravitons. Okay. Now, you could ask, what is the, this is all okay, but it looks very sort of ugly. Some funny parameterization of these things in terms of gauge non-invariant variables. Is there a gauge invariant way of characterizing these alphas? Okay. And here I've given it for the graviton case, but it's very similar for the sorry, the photon case, but it's very similar for the graviton. In fact, if you just think of F here as a formal object, which is pi epsilon j, p mu epsilon nu minus p nu epsilon mu. This is same for gravitons as well as photons. Okay, the alphas can be given in terms of these Lorentz invariant and manifestly gauge invariant combinations of these polarization vectors by these formulas, where F3 is, P3 mu epsilon 3 nu minus P3 nu epsilon 3 mu. And these epsilon perpendiculars can also be expressed completely in gauge invariant, in terms of gauge invariant variables. Okay. There's a subtlety for how these alphas transform under. Okay. I told you that these epsilon perpendiculars were epsilon perpendiculars and these alphas were data characterizing scattering polarizations. And we're going to impose invariance under permutations. So I have to know how epsilon perpendicular, the momenta, and alphas transform under polarizations. At first sight, you might think that's obvious, right? Under permutations. At first sight, you might think that's obvious because permutations just switch around the particles. So each of these three objects, the momenta, epsilon perpendicular, and alpha, should just transform in as the defining representation of S4. And that's certainly the case for the column of momenta and the column of epsilon perpendiculars. However, there is a subtlety given the fact that there is a certain, because of the fact that we made some arbitrary choices in defining alpha. There's a subtlety in the transformation properties of alpha under permutations. This transforms in this defining representations times an anomaly type factor, including -1 to the sine p. This took us a long time to figure out. Shubham was the guy who nailed it. Okay. And this it proves very important in getting the details right. Okay, I won't dwell on this. Okay, so one way of parametrizing the truly independent data of your scattering. So maybe I should have given a little more motivation for this exercise. So far I was telling you about scattering in terms of these covariant polarizations epsilon. The difficulty of dealing with these covariant polarizations epsilon is that we want to deal with only gauge invariant scattering amplitudes. That the epsilon is not completely free data. It has to obey this gauge invariance condition. Okay. What we've managed now to do is to distill our scattering amplitude in terms of purely free data. These epsilon perpendiculars and alphas are free data. They can be freely specified to specify scattering amplitudes. Okay, there are no further constraints on the data. Now, the key thing that makes this way of thinking, useful is the following. It turns out that every scattering amplitude that is a polynomial in epsilons and p is also a polynomial in alphas, epsilon perpendiculars, and p. This statement is far from obvious. It's far from obvious because epsilon perpendicular here has, the expression for this has terms st and u and so on in the denominator here. Similarly, alphas have terms that are in the denominator here. However, we have checked by long and detailed explicit calculations that the statement is true. There's probably a very simple, elegant proof for the statement, but we've not found it. Okay, but we've checked it 100%. So we know this is true, though I suspect there's a very simple way of saying why it's true. Now, what does that mean? This is very important for the following reason. Suppose we define a new module structure, which is the module of all objects that are built out of these alphas and epsilon perpendiculars. And on top of that, we put polynomials of st and u. We call this the bare module. All such structures will not be classical local matrices, because the matrices that we wish to classify are those that are polynomials of epsilons, these covariant epsilons, and st and u. However, this result tells us that while every element of this bare module is not part of the physical scattering module space, the converse is true, that any actual scattering amplitude is an element of this module. Now, the reason this is useful is as follows. Okay, the reason this is useful is as follows. It's useful for the following reason. It's useful because the module, this bare module, because since epsilons and alphas have nothing to do with ST and U now, nothing to do with momentum anymore. Okay, these are just completely independent data. This bare module is obviously a free module, whereas the physical scattering module may not be. So what we managed to do by this construction is find a simple mathematical structure, namely that of free modules, within which the physical structure, namely the actual physical scattering module, is embedded. And now the question of, within this very simple mathematical structure, these free modules, how the physical scattering amplitudes are embedded as modules is a clear, clean mathematical question that we can address. Okay? All we need to do is to find the expressions for the generators of our physical modules in this module. And then since they're embedded in a well understood mathematical structure, we can answer the question of whether the physical module is free or not, completely enumerate this physical module. Okay, so I've said this in an equation here. Now, to complete our program, what we need is to find expressions for the physical module generators as descendants of the bare module generators. Now, this program is a long and detailed one. One of the things we do is to completely classify the bare modules. We completely classify its generators, count them. I have in my note in my lectures how this analysis is done, but we'll skip that, and I'll just give you the final results. Okay. For the bare modules, and maybe Shuman will tell you about some of how this works. Okay, for these bare modules, in the case of photons and gravitons, we've done it separately. We've counted the number of generators. Okay, and for photons, for d greater than or equal to 8, for every dimension d greater than or equal to 8, the number is always 7, and then the number of parity even generators goes like this, and parity odd generators goes like this. You see, it's an interesting table with some detail depending on dimension. For gravitons, the corresponding numbers go like this, and for even generators and for odd generators go like this. Now, we've not just counted these bare module generators, we've constructed them. We've got explicit expressions for all of them. And by using the explicit expressions, we've classified these bare modules into how many of them are in which representations of S3. And you get the following table. Okay. Again, I don't expect you to pay attention to all the details here. The point is just to show you that we know it very completely. So the bare module structure we have under complete control. Okay. Now, I will just skip. Okay, I will just skip the analysis for how we worked out how these physical modules are embedded inside the bare modules and characterize them. We use Lagrangian's the sort of important effect in this procedure, but this is just the final result. In d greater than or equal to 5, it turns out that there are as many generators of the local module as the bare module. The local module is the module of physical S matrices, where this bare module was this more primitive structure within which the structure was embedded. Okay, and in such a situation where the number of generators match, it's easy to work out a condition to determine when these local modules, these actual S matrix modules, are freely generated. That is a condition on the coefficients. That turns out, you see, I told you that these coefficients, that the physical module generators can be written as linear, as descendants of the bare module generators. So these Pij's of S and T, if you know these, turns out you can show that provided the determinant of this Pij of S and T is non-zero for any S and T, then the physical S matrix module is also freely generated. Okay. Now, for this to be 0 for every asymptote is a very stringent condition, and in d greater than 5, when this condition is met, that the number of bare module and physical module generators is equal, this condition is never met. We showed this, and therefore the modules of physical generators are also free, and so that's an enormous simplification. The structure of S matrices in 5 and higher dimensions from this point of view is very simple, because all you need to do to specify the structure of S matrices is specify their generators. And then you can get the generators and their descendants freely generate the whole set of S matrices. There's no overcounting. Okay. Fine. Let me pause here for questions or comments. I'm sorry if this has gone too fast and was too boring. I know it's technical, but sometimes you need to do some technical stuff to get to the interesting physics. Sorry about that. Questions or comments?
Yeah, so Shiraz, I had a question.
Yes.
So this bare module
Yes.
in 4 dimensions,
Yes.
is it somehow simply related to the helicity formalism?
Okay. Yes, it should be. It's certainly parameterizing independent data, just like the helicity formalism does. At some point, we tried to find explicit connection, and for at least many amplitudes we found it, but it was a bit. Yeah, I think the answer is yes. Though we've never dotted all the I's and crossed all the T's to find the explicit map between the two. Yes, the answer, of course, is yes, because both of them are characterizing independent data.
I don't see any other questions.
Okay. Okay. Fine.
So Shiraz, you'll take another half an hour.
Yeah, half an hour will be more than enough. I'll stop in like 15 minutes. I'll stop for questions.
Okay.
I'll try to. Right. Okay. So, fine. Now, one last thing I wanted to remind you of. Okay, this is less technical and maybe more fun. Okay. The last thing I wanted to remind you of is that there is a one-to-one correspondence between S matrices and Lagrangians, modulo field redefinitions, and modulo field redefinitions and modulo momentum conservation, and equations of motion. Field redefinition, equations of motion, same thing. Okay, so I want to remind you of how that works. Okay, consider a Z2 invariant scalar field. Okay, consider a Z2 invariant scalar field which has a kinetic term and some interaction terms. Okay, now if we take the scalar field and we perform a field redefinition of the following schematic form, phi, the change in phi is some cubic expression in terms of phis. Okay, then up to terms that are sextic or higher, the change in the Lagrangian is just the change in the Lagrangian always is the equation of motion times delta phi, right? Because that's how we get the equation of motion. That the equation of motion of the Lagrangian is the variation with respect of the Lagrangian with respect to fields, the coefficient of that variation. So you get equation of motion times delta phi. So equation of motion had both in this theory had both a linear term and a cubic term. But the terms that are cubic and higher will give you terms in this equation that are sextic. Okay, so keeping only terms that are quadratic, the change in the Lagrangian is del square phi, which is the equation of motion that came from the kinetic term, times this delta phi. Okay, now clearly two Lagrangians should be thought of as equivalent if they differ only by field redefinitions. So any term in a Lagrangian that differ, any two Lagrangians that differ by such terms, as long as we're concerning ourselves only with 4-particle scattering, are to be regarded as identical. Okay. Also, if you've got a term in the Lagrangian that's a total derivative, it's a derivative of some form. You know, it's a derivative of something. This, of course, does not change Scattering amplitudes does not change classical physics, will not contribute to scattering. So these two operations are operations you can do in Lagrangians without changing the physics of the Lagrangian, in particular without changing the scattering amplitude. Okay, but now what are these two operations in momentum space? In momentum space, our Lagrangian can be written in this form, and the first operation, namely taking a total derivative, would be multiplying this Lagrangian with k1 plus k2 plus k3 plus k4. Okay, and this operation here, namely doing our field redefinition, would be adding terms here where at least one of these terms had a k1 squared attached to it. Okay, so if we take these terms L4 of k1, k2, k3, k4, and regard these L4 of k1, k2, k3, k4 L4s that differ either by terms that are 0 when k1 plus k2 plus k3 plus k4 is 0, or by terms that are 0 when either k1 squared or k2 squared or k3 squared or k4 squared is 0. Okay, then that is the set of, that is in one-to-one correspondence with the set of Lagrangians, modulo field redefinitions, and modulo total derivatives. But that is also precisely the data that classifies S matrices. Like S matrices are the interaction terms in the Lagrangian, except the two that we always evaluate these interaction terms on shell. So k1 squared is set to 0. Two terms that differ by k1 squared are set to be equivalent. And they're always evaluated on momentum conservation. So that two terms are equal as long as they differ by terms that are 0 once you set k1 plus k2 plus k3 plus k4 is equal to 0. Okay, so this business of classifying S matrices is the same as the business of classifying Lagrangians, modulo field redefinitions, and modulo total derivatives. Okay, now let's skip much of this. Let's skip much of this. What I wanted to tell you is that we have a second way of counting all possible S matrices. Okay, we have a second way of counting all possible S matrices, and this second way is by this Lagrangian method. Okay, let me very briefly tell you how that works. Suppose we were doing it for scalars. Okay, if you were doing it for scalars, all possible Lagrangians that are quartic in the scalars are any products of elements like this, 4 elements like this. But then you have to put this module, you have to set terms that have del square on phi to 0, those don't count. And you have terms that are total derivatives to 0, those don't count. Okay, so the problem of counting all Lagrangians, modulo equations of motion and modulo total derivatives, is a separate counting problem that one can do. Okay? Not using any of this module structure and so on. And one way of doing it is just to enumerate all polynomials of such fields that are quartic in such fields, weight them with respect to a chemical potential for SOD angular momentum, and finally impose the condition that you're counting only singlet states under this SOD angular momentum by doing an integral over the SOD Haar measurement. Okay, this is a platistic counting problem of the form that is has been studied before in certain contexts, and this is another way of counting all possible S matrices graded by derivative order. Okay, what you're doing is counting all possible interaction terms, modulo terms that are 0 by equations of motion, modulo terms that are 0 because they're total derivatives, and right at the end projecting onto the space of SOD invariants, because Lagrangians are always SOD invariants. Okay, so one way of enumerating all of your S matrices is through this module structure. Find the generators and find the partition functions for the space of S matrices using these modules. Another way of enumerating these S matrices is by using this platistic idea, so counting Lagrangians. Now, both of these are slightly involved problems. For that reason, it's useful to have two different methods, so that when you get this enumeration, you know that you're correct if the two different methods agree. And that was the final thing is that they do agree. Okay. So for instance, both methods give us the following. If we try to enumerate the partition functions of all S matrix elements, okay, for graviton scattering, as a partition function, each S matrix elements that's of dimension delta is weighted by an x to the power delta. We compute the following partition functions, both from this module method and from the plethistic method. You can say they're quite involved functions. The fact that they both agree give us complete confidence that it's all correct. Okay. The net result of all of this is the following. We have a completely explicit and completely satisfactory classification for all these S matrices, these polynomial S matrices. The good way of getting the explicit structure of these S matrices, and we have completely explicit, we can not just count them, we construct them. The good way of getting the explicit structure of the S matrices is through this module method. Another good way of counting them is through this Lagrangian method. Both give us the same. And so I'll just show you, just run through some results. Okay. So the most general gravitational S matrix is sum of various pieces, all of which I've listed in this, on this transparency. Was this the gauge boson? No, graviton, yes. The most general for graviton S matrix is sum of structures, all of which I've listed in these transparencies. Okay? Everything is completely explicit. What this one, for instance, multiplies a free function of S and T that has certain symmetric properties. This one multiplies another free function of S and U that has certain symmetric properties. So any such function gives us a legal S matrix, and no S matrix is counted twice. So this gives us completely explicit classification of all polynomial gravitational S matrices. Okay, and this classification has been checked and counted by these two different methods. Okay, I think that's all I'm going to say about the counting problem. I'm sorry I didn't have the time. I planned the time so badly I didn't have the time to go through all of it in detail. The last 5-10 minutes, what I'm going to tell you about is how we use this. Okay. Any questions? Yes.
Yeah. So you would be could you send these slides to us? Maybe
yes. I'll send them to you.
The school site. Yeah.
Yes. Okay. I see from the fact that there are no questions that I'm not being understood, which is depressing. But okay, what to do? Okay. Let me just give you the last 5 minutes of the punchline again. Now that we have constructed this, we've got this full construction of this gravitational structure of the structure of these S matrices. We can now step back and ask, okay, which of these S matrices obey the CRG conjecture? Okay, so those of you who stopped following but are still here, please tune on again, because now we're coming back to the physics. Okay. Now we can ask which of these S matrices are CRG allowed? Which of these are S matrices that don't grow faster than S square at fixed T? Okay. And the result that we get, first let's turn to polynomial S matrices. Okay. The result that we get is the following. There is only one polynomial S matrix that you can make out of 4 gravitons. Okay. That is CRG allowed. And this polynomial S matrix is very simple and it's given by this structure. So wedge product of epsilon 1, wedge epsilon 2, wedge epsilon 3, wedge epsilon 4, wedge P1, wedge P2, wedge P3, the whole thing squared. You might wonder whether there's some symmetry breaking here because I've chosen to wedge with 3 P's, but you can convince yourself that using momentum conservation, the wedge of any 3 P's is the same. Okay. This is a 6 derivative S matrix, which follows from, which is CRG allowed, and it follows from the Lagrangian that can be written like this. Okay, and this Lagrangian here, is the Lagrangian of a term that is sometimes called the second Lovelock Lagrangian. Now, look at this S matrix here. This S matrix is a wedge product of 7 different vectors. If we were in, and then squared. If we were in 6 or lower dimensions, okay, this wedge product here would just vanish because you cannot have the wedge product of 7 different vectors in 6 or lower dimensions. So this S matrix only exists in 7 and higher dimensions. In fact, you can see the same from the Lagrangian here. You can see the same from the Lagrangian here, that this Lagrangian here is either a total derivative or is identically 0 in 6 and lower dimensions. Okay, so in 6 and lower dimensions in particular, our classification, combining this classification of polynomial structures with the and then asking which of these is CRG allowed gives us only one possible, it gives us no answer. 6 and lower dimensions, there are no CRG allowed polynomial S matrices.
Okay, Shiraz, I have a question.
Please, Ashok, sorry.
Yeah, so it looks like that these kinds of Lagrangians are the ones which allow initial value problem, right? Lovelock.
Yes.
So are these unrelated, or these are, you think these are related?
Okay, that's an excellent question. Now, there's an even simpler Lagrangian of this form that allows the initial value problem, namely the Gauss-Bonnet Lagrangian. That Lagrangian is made up of 2 of these R's with a sort of similar structure. Okay, now I will explain to you that the Gauss-Bonnet Lagrangian actually is not allowed by CRG conjectures. Gauss-Bonnet Lagrangian violates CRG. Okay, and it also it was also disallowed by the fact that it was also disallowed by CMZ. Gauss-Bonnet gives rise to a 3 graviton scattering amplitude, and the 4 graviton scattering amplitude that you get by sewing this 3 graviton scattering amplitude on a pole and then making it 4 graviton scattering amplitude, A, violated CMZ's causality constraint, B, also turns out to violate our CRG conjecture. Okay, so I suspect that even though these things look like they have a good initial value problem, they're not really allowed. We saw the fact that it was disallowed for Gauss-Bonnet because it could contribute via pole exchange to 4 graviton scattering. This Lagrangian here will contribute via a pole exchange to 6 graviton scattering. And I believe that if you are able to study that 6 graviton scattering amplitude, you'd find a pathology there from this. So it looks like it's allowed, but it's not.
Okay.
Is my guess.
I see. Okay.
Okay.
Okay, thanks.
Yeah. Okay. Excellent. Now I've given the argument here for how this works, and doesn't matter. For how we can prove that this is the only allowed structure. Forget that. You can prove it. Okay. Now let's turn to the pole exchanges. So far I've told you about this.
Maybe can I ask the question in the reverse way? That can you show that if it doesn't admit it to an initial value problem, that it necessarily violates CRG conjecture?
I don't know how to show this, but it's very possible that it's true. I don't know how to show it. It could well be true. You see, let me say one thing that I should have maybe said more clearly. There are some kinds of terms, that would definitely violate everything. Those kinds of terms that are terms that give you poles and wrong signs poles and propagators. Okay, so if you added some higher derivative term and you truncated with that higher derivative term and it gave you the wrong sign pole and a propagator, then you're certainly going to violate everything. Now, neither Gauss-Bonnet nor this term are of that sort, because Gauss-Bonnet turns out, though it's quadratic in Riemann's, it turns out to at the quadratic order to be a total derivative. Contributes first at cubic order. And this term here was explicitly cubic, so clearly it doesn't contribute to the propagator around flat space. Okay. So one way of ruling out terms is but if you had some other kind of quadratic expression which had some higher pole, that would be ruled out by the pole condition. Okay. Now, if you had some higher derivative kind of Riemann structure that that didn't have a good initial value problem, it could well lead to the analog of this funny pole around some background that is not flat space, where you absorb some of the Riemanns in the background. And so it could well be that that would be a way of proving what you want, namely that you transfer the problem into the quadratic part and see clearly that there is an immediate problem by working with general backgrounds. But this is a vague idea. I don't know if it's correct.
Okay, thank you.
But I think it could well, it's likely that what you're saying is true.
Okay.
Okay, fine. Good. So far what we did was to look at the polynomial parts. Okay. Now let's start looking at the pole parts. Let's first start with gravity.
Shiraz?
Yes.
There's some set of questions in the chat.
Yes.
So one is to ask for a reference for these classifications.
Okay, the reference classification is paper 1 in my list of references. Okay, right at the beginning of this talk, I had 3 references. The first of these is the classification. It does the classification in more detail than you'd want to see.
Yeah. Okay. And then there's a clarification on this initial value problem question that
Yes.
Ashok asked. So if the Lagrangian does not allow initial value problem, is it possible to define a scattering problem? That is, define initial state, final state, and ask for an S matrix.
Yeah, maybe in some deep way it isn't. But you see, at the level of what we're doing, all we're doing is taking 4 plane waves and looking at the overlap through that contact structure. And at that level, there's no problem with the scattering error. Now, it could be that in some deep way, there's a causality, whatever. There's some deep way, there's a problem, and this is what is also somehow related to non-CRG. But at the level of actually doing a computation, you don't see that problem. You're just doing a tree-level computation with this term, which you can do, right? You just plug in the interaction Lagrangian with the on-plane waves.
Okay, I don't see any other questions for now.
Okay, I'll really be done in like less than 5 minutes. Okay, so fine. So far we've talked about these polynomial interactions. Now there are also there are also the pole exchange interactions. Okay, first let's look at exchange with gravitons themselves, and then we'll turn to exchange with other particles. So now I told you that these pole exchanges are classified by these 3-point functions, these 3 graviton scattering amplitudes. Right? The 3 graviton scattering amplitudes are just, we saw them early in these lectures. There's Einstein, Gauss-Bonnet, and Riemann. Now, there's something you can just do. Actually, even this, I cannot understand why, but before our paper had never been actually done. You can just take this A times Einstein plus B times Gauss-Bonnet plus C times Riemann cube and just compute the graviton scattering amplitude, the full S matrix for this Lagrangian, including the pole exchange. Okay, and and we went ahead and did this. Okay, and then you compute that S matrix, and you can just see that while for the Einstein action. Okay, when you use the Einstein action, when A is the only non-zero term, this thing is CRG allowed. If either B or C are non-zero, you get CRG violating terms. So that's another nice thing. Precisely where, and the CRG violation comes from the whole structure. The gauge invariance links the pole and the contact terms. Okay, precisely where the causality argument of CEMZ goes bad, CRG also goes bad. Okay. What am I doing? Okay. Now, when I tell people about this, sometimes I get the following question. Okay. When I tell people about this, I sometimes get the following question, and actually this question is the heart of some confusion in the original chaos bound paper, which made some not completely correct statements. The question goes as follows. Isn't it true that the Rayleigh scaling of an exchange amplitude is determined completely by the spin of the exchange particle? Okay, isn't it true that the Regge scaling of some exchange amplitude is determined completely by the spin of the exchange particle, and therefore, isn't what you're telling me a contradiction? You're telling me that if I just change the 3-point interactions which govern the exchange of this particle, you're changing the Regge scaling of the behavior. You're making a CRG amplitude, an amplitude like Einstein, the one governed by Einstein gravity, which was CRG allowed. You're turning it into a CRG non-allowed amplitude. Isn't it true that this is impossible? Because I've read as an undergraduate that this Regge scaling is determined by the spin of the exchange particle. And indeed, it's true that if you look at exchange amplitudes, there is one channel, namely, people have different names for it, but I call this the T channel, because in this channel, the denominator is T. Okay. In the T channel, indeed, it's true that the Regge scaling of this amplitude is like S to the power j. But the full scattering amplitude is crossing invariant. That in addition to the T channel, there's the S channel and the U channel. And it's not true that the growth of the scattering amplitude in the S and the U channel is determined by just the spin of the of this particle. And in fact, it's those channel contributions that give you CRG violation. Okay. Now note that the T channel contributions are special. They are the contributions which, there's this general fact in S matrix theory that the scattering amplitude in T space at fixed S and the scattering amplitude in impact parameter space at fixed S are related to each other via a Fourier transform. Okay. Now, if you've got an amplitude that's analytic in T, therefore it clicks only at zero contact when you do the Fourier transform, because analytic terms map to contact terms under Fourier transform. Whereas, so the terms that violated the CRG conjecture were analytic in T, but not in the T channel. The T channel has 1 over T, so it's not analytic in T. But not in the T channel. Whereas the terms that were non-analytic in T and that you could see at non-zero impact parameter did not violate the CRG conjecture. This is why CEMZ did not see this violation. CEMZ were very aware of, they liked the CRG conjecture. In fact, they gave the signal model for it, right? And had they seen that there was this CRG violation from this kind of scattering, that would have triggered, I think, had set their antennas up. But they were always concentrating on working on scattering at non-zero impact parameter. And this is why they didn't see this violation. This is violated, but at terms that are that you don't see at non-zero impact parameter. Okay, fine. So already at the level, if you just take the graviton exchange, already at the level of graviton exchange, you see something special about Einstein gravity. Now let's look at the exchange of other massive particles. Because we've completely understood the structure of graviton massive particle, we can completely characterize all such exchange diagrams, and we can show. And a key element that goes into this is the fact that the graviton other particle was 2 derivative higher. It was 4 derivative higher. We can show that all such exchanges also violate the CRG conjecture. Finally, you might be worried that maybe exchanges violate the CRG conjecture and polynomials violate the CRG conjecture, but you can find some linear combination of exchanges or some linear combinations of exchanges and polynomials that together don't violate the CRG conjecture. Now, we can show that the violation of CRG conjecture in an exchange can never be cancelled by a polynomial. It can be cancelled by another exchange diagram, but only if the exchange diagram is of the same spin and comes with the opposite sign. But exchange diagrams have a definite sign in a theory with unitarity because they come with 3-point function square. And therefore, once we input this contribution of unitarity, the condition of unitarity, the CRG violation between two exchange diagrams cannot cancel against each other. And therefore, the end result of all this analysis, so I've given lots of analysis of these statements, therefore, the end result of all of this is that using our complete classification, we can show that in D less than equal to 6, there is no scattering amplitude other than Einstein gravity that is CRG consistent. In d greater than equal to 6, there's exactly one more. That's this second Lovelock, Einstein plus second Lovelock. Okay. This then basically establishes conjecture 2 for graviton scattering at least in d less than equal to 6, provided you buy the CRG conjecture. Okay, that's the end of my lecture. Sorry for having gone so long, and sorry that this lecture was so technical. Perhaps I should have, Schumann, when he was giving me advice on this lecture, said skip the modules. Maybe I should have listened to Schumann, but okay. That's it. Thank you.
Yeah, thanks, Shah. So there is one question by Aninda in the chat, which is that in the
let me just answer the question.
Yeah.
Maybe I can answer this question. So, in the previous lecture, just before you all, in Simon's lecture, we were told that if we consider 2-to-2 scattering of gravitons, then the Einstein term and Riemann cube, they both contribute to 1 over STU. 1 over STU. But it seems like what you are saying, you are saying that the statement is not right.
But I didn't understand. Say it again. So the Einstein term and the Riemann cube term both contribute what? Could you say what you said again, please?
Yeah. So we were told that the Einstein term contributes to 1 over STU, and Riemann cubed actually contributes like ST by U. ST by U. That's what we were told.
Oh, really? I mean, Einstein term gives you an, okay, there may be many ways of saying it, but the leading contribution of Einstein is S square by T. And then, of course, there's a T squared by S.
So if you factor out this.
Yeah, you can put them together into some STU plus other stuff. Yeah. But it's most useful not to do that. If we're interested in Regge scaling, it's S squared by T. The Regge scale.
Up to that. So do you remember what the Riemann cube precisely contributes when the Einstein term contributes as S square by T?
Well, yeah. So the Riemann cube term will contribute. I may have it written here. So the Riemann cube term will contribute effectively like STU. This is not. So the Riemann cube term is not giving you. Okay, there are two things I should say. Okay, I was very fast and I didn't say one important thing. The important thing is this: there are two Riemann cube terms. There are two inequivalent Riemann cube terms in the Lagrangian that one can write. One of these two Riemann cubes contributes to 3 graviton scattering. The second one is a particular combination of Riemann cubes that is a non-trivial Lagrangian term, but whose expansion to cubic order is 0. Its expansion starts at 4th order and higher. Okay? That special Riemann cube term is this guy. Okay? So this guy does not contribute to 3 graviton scattering at all, even though it's a Riemann cube term. It contributes only to 4 graviton scattering and higher. Okay, so when in the previous part of the lecture I was talking about Riemann cube, I was talking about generic Riemann cube, which is not of this special structure. That contributes to 3 graviton scattering and will contribute. Now I don't remember exactly the exact structure. It's in our paper. We've explicitly computed that's the C term here. That's the C term in this. Okay. Or the C term, So we've explicitly computed the S matrix for that term, but that will have poles and will have some numerators. Okay, and that guy grows. If I remember right, and maybe Shuman or Shubham can correct me if they're here. I believe that one grew like there was a term that went like S to the 4.
I see.
Yes, at least in the cross between. Yeah, I will misquote if I say it. Sorry, was that your question?
Yes. Yeah. No, that's right. Okay. Yeah.
But it's very important that the Riemann cube that is being allowed here does not contribute to 3 graviton scattering.
Okay.
Yeah. Okay. Great. Other questions? Yeah, Raghu has raised his hand.
Hi, Shiraz. So just to do an example for the pole exchange.
Yes.
So let's say the intermediate particle was a scalar.
Yes.
Then the term in the Lagrangian is phi times Riemann squared.
Yes.
So when you saw the thing into a 4-point vertex, what is the S scaling of that particular diagram?
Right.
Is it S to the fourth or?
Yes, I believe it's S to the 4. You see, by dimensional analysis, what we will have is the following. We will have 4 derivative times 4 derivative divided by something.
Right.
Okay. Now, if we divide by the term that is just t, that would have been naively the fastest scaling. But that term does not that term does not scale badly, because that is just determined by, that's t channel is just determined by the fact that it's S to the 0. Okay. However, the other terms, which were some 4 derivative times 4 derivative divided by let's say an S. Okay, so that would be effectively 3 powers. I believe there is a term that goes like S cube. Sorry, not
S cube. Okay.
Yes, I believe there's a term.
I see.
Yeah, right. The worst possible could have been S to the 4, because that could have been 4 derivatives times 4 derivatives, so like S to the 4 divided by t. Okay, but that term is not bad because it's governed by the spin of what's exchanged. Okay, it's a subleading term that goes bad, and I believe that's S cube. Okay,
thank you.
Yeah. Right, Raghu, were you satisfied with the answer to the question about 2 derivative? The answer to the question you asked in the first lecture, namely the fact that you never can have 2 gravitons scattering to anything else in a 2 derivative gravity is just a fact about that you can prove by classification.
Yeah, so Raghu says that, yeah, he sees that.
Okay, good.
Are there any other questions? Sorry. Oh, I'm not. So, Raghu, did you want to ask further question? Okay. Are there any other questions that
Shivam Sharma has raised?
Yeah.
Yeah. So maybe this is a quite naive question, but in this whole analysis, we take an asymptotically flat space and understand the CRG conjecture and S matrix is there. But do we have something about the asymptotically AD spaces in the context of maybe somewhat related to ADCFTs?
Okay, it's a good question. Right. For instance, my attempt at giving you a clean argument for the CRG conjecture proceeded through ADS, right? And that proceeded in turn through the chaos bound. Now, it's a little bit like this. If you wrote down a general 4-point function on the CFT side that obeyed all the conditions of crossing invariance and kinematics, conformal kinematics, but did not worry about unitarity, you would be able to generate correlation functions that violate the chaos bound. One simple way to do that would be to take a CRJ violating interaction in the bulk and use ADSC to compute these correlation functions. So the most straightforward answer to that question is that the analog of the CRG conjecture is the chaos bound, and the analog of bad theories are theories that violate the chaos bound or theories that are not unitary. I think unitarity on the CFT side is sort of playing an important role. Of course, the analysis of Hartmann and collaborators, including Sachin, has shown there's a tight connection between unitarity and causality. Right, the connection is the following, that if you take any correlation function in Euclidean space that obeys all good conditions, including reflection positivity, then it will analytically continue the correlation function in Minkowski space that is causal. And so if you violate causality, you also violate unitarity. So unitarity somehow plays a key role in CFTs, causality as well. Okay, I hope that was the.
Yeah. Okay. Thanks. So I mean, but one could I mean, we have the three forms of the conjectures, right? I mean, 1, 2, 3, and we could do the same thing with the ADS.
Okay, excellent question. So on the ADS side, yeah, let's take conjecture 2. Okay, conjecture 2 translates to the following statement in ADS. Consider a large N gauge theory whose single trace operator spectrum, okay, includes only a finite number of operators that have non-zero OP with 2 T's, whose 3-point function is non-zero at leading order large N with two stress tensors. Okay, consider such a theory. Okay, then in such a theory, at least conjecture 2 sort of suggests, if not establishes, that the TTT correlation function, TT correlation function of any such theory, if it's a good unitary theory, has to be that comes out of Einstein gravity. It's the forced for stress tensor, and in fact arbitrary number of stress tensor correlation functions of such a theory is there's a unique structure for that. That's Einstein gravity, the one that you get out of Einstein. This is what it suggests for CFTs. And really, I think one could probably prove this along the lines of what we did using the chaos part. So this would be the implementation of this in CFT. Was this your question?
Yeah. Okay. Yeah. Thanks.
Yes.
Okay. Are there any other questions, comments? Okay, I don't see any further questions, and and so we will I mean, you can also put the questions in Slack and so on. So Shiraz, you are like logged into the Slack, or?
I'm not actually. I didn't even know there was a Slack. I missed the mail. Yeah. So please send me the credentials. I'll log in.
Yeah. Okay. Yeah. So
and I'll send you my slides. And of course, you guys have Shuman's tutorial session over the weekend. Shuman, I think, is planning to go through some of the technicalities with you in some in some detail. So if this lecture was unintelligible, please ask him questions and also listen to his. Thank you. I'll send you my slide.
Okay. Yeah. So please do so. Okay. So then thanks everybody. So the next talk we are having at 7:30 Indian time by Surjit Rajendran. So see you then. Bye.
Thank you, Shiraz.
Thanks, Venta.
So actually, Shiraz, can I ask you a question? It's a bit late, but
of course.
It's just one thing. It just
yeah.
That like I mean, it's a question about just the general tenor of these results.
Yes.
I mean, I'm not so like when we initially talk about like non-renormalizability of gravity, right? I mean, usually we say that, oh well, you do these loop diagrams and you get these divergences, and you have to put infinite number of counter terms. You get all sorts of higher derivative corrections, and it's completely uncontrollable, and you will have infinite number of terms, and like you can't like do anything with it.
Right.
So that's of course a question about loop computation. So it's a different question than what you're asking.
Right.
But there seems to be some kind of a philosophical clash between this kind of a result and that kind of a result. That though there's a logical contradiction that somehow the classical gravity has so much rigidity, but quantum gravity is completely uncontrollable. So somehow these two statements are or philosophically opposite.
Yes. Yeah, let me just add to what you said. When I started studying gravity, I was under the impression that it was very hard to make a consistent quantum theory of gravity. Partly for the reasons you mentioned, the renormalizability and just cutting off those divergences in a way that's unitary. I was given the impression that was a very hard problem. Whereas studying classical gravity was an easy, generalizing classical Einstein gravity was an easy thing. Just add any term to the Lagrange. That's diffeomorphically invariant. Maybe don't do stupid things, but there'll be lots of leeway classically. But it's quantum mechanics, these loops, these divergences, and so on, that give you the constraints. This is, roughly the sense I got as a PhD student. Okay. Now let's go and look at the actual evidence. By evidence, I mean string theory. Let's look to ask for how many quantum scattering amplitudes, how many different quantum scattering amplitudes do we have? I take an S matrix for gravitons and I allow cuts. And how many different formulas do I have? And I take the S matrix for gravitons and I allow only poles. And how many different formulas do I have that I get by taking a justifiable limit of string theory? For this purpose, let's say that string theory is correct, right? I mean, is consistent. So the answer to that question is you got zillions of amplitudes with cuts, because every compactification of string theory gives you one of those. Okay, but the number of answers that we have with just poles is like 3. Okay, so I think that the evidence, irrespective of these analyses, you just look at the evidence and you see that thing was somehow backwards. It should be that it's very hard to make classical theories of gravity, and quantum mechanics gives you leeway to move around, rather than the other way around. Now, this is really surprising. I agree with you. It's totally surprising. But the kind of analysis that CEMZ did and that we are doing shows that it's not crazy, right? You can put reasonable constraints and immediately cut down the space of allowed classical things. As soon as you add loops, the fact that you've got arbitrarily high spin exchanged in those loops changes these analyses very much and completely weakens your results. Maybe I can say one more thing, Loga. I don't know if this is what you were after, but let me say one more thing. The one more thing is that, you see, we often say that when we try to quantize gravity, we can find a very rigid structure like string theory. Okay? But if you think about it, the quantum mechanics happens on the world sheet. Even for tree-level string theory, we find a very rigid structure, right? The structure, the rigidity comes about even when string theory is the tree level. The loop character of it, okay, was not that important. So somehow it was always true in string theory that we saw lots of constraints even classically. The fact that we see more constraints classically is this other remarkable statement that there is this consistent truncation of this universal sector. That the other stuff, the stuff in the compactification, doesn't talk to this consistent truncation. I think that is a key thing to understand. I wonder if there's some symmetry analysis associated. Sorry, I don't know. These were incoherent thoughts that were put all over the place, but please respond.
But a lot of rigidity comes from modular invariance, right? Which is about one loop. But
a lot of rigidity comes from modular invariance. That is true. That is true. That is true. But modular invariance is very tightly related to single valuedness of correlation functions on the sphere. Right? For instance, when we do toroidal compactification of you try to make all possible heterotic strings. You get constraints on the Narayan moduli space, either by modular invariance or by demanding single value of the vertex operators. But I agree. It's true that having the CFT well defined on a torus is important. But actually doing the moduli integral over that thing to generate the loops was not really very important, right? Or was it? It's true. What you say is true, that the constraints seem to come from the fact that you have a CFT, worldsheet CFT, that is well defined on every genus manifold. And then you work with that CFT on the sphere. And if you say that was loops, in some sense it's true. That it was, maybe what you want to say is that it was quantizable. And that it is a classical theory that came as a limit of the quantum theory. But the same structure determined the quantum theory. I mean, wasn't like the huge additional constraints, I think, that came from. Okay, I don't know. I've said what I have. Yeah. But please respond, Loga. Please.
I don't know. I just, it seems a bit this thing, because at least we would think that if it is like a usual effective theory, there should be like you integrate out stuff, the loops should become tree level things in low energy effective field theory. And I mean, at least it's kind of, and you should get a lot of, like effective field theory that way. But you don't seem to get a lot of it.
Right, but right. But notice that we're demanding classicality. Okay, so you would get a lot of effective field theory if you also had loops. So for instance, the M theory effective field theory is completely unconstrained by what I'm saying. It's only in this classical limit that this rigidity emerges.
But usually you would expect a lot of classical effective field theories also.
I wonder, would you really? One way of getting classical physics is by taking your, suppose we didn't have string theory at all. One way of getting classical physics would be to take the Planck scale to be very large, right? Or to go to very low energies compared to Planck scale. And then just dimensional analysis would tell us we'd get Einstein. Now, the question is, when you also have this string coupling, does that change very much? I don't know, right? Have you followed this kind of thing Simon Carenho and collaborators try to do?
Yeah, so Simon was just telling us this morning that there's one, maybe that's one way to understand this question, which is that in some sense that, like you might think that you can take a heavy particle, interacting with gravitons and then integrate it out and get some new scale, and then you can get a classical action, but it doesn't really work, because I think what CRG conjecture is saying is, like what Simon was telling us is that in some sense you can have a heavy particle, but it can't like interact strongly with gravitons. Like it still interacts with G Newton. So when you integrate it out, you still get something which is M Planck suppressed and not not any other scale.
Yes.
And hence like you can't take a classical limit until like you don't get if you take M Planck to infinity, you kind of kill that also.
Yeah. And what's really important is this, that if they have this desert kind of scenario, right? I mean, where there's a UV scale and there's this place in between. Now, if you populate that region with massive particles, so as to try to get some new scale, you will violate CRG conjecture. That's basically what this pole exchange business is saying. And then you also violate their fancy CRG conjecture, right? They put it in the deep UV, but it's not very different. It's basically CRG. Yeah. Now, so to understand why Simon's results are correct, again, you have to understand that CRG, right? the UV condition on scattering. Right, that's the key physics input into what he does. There's unitarity, there's dispersion relation, and then there's some very high energies, you put some condition. And roughly speaking, that condition just filters through to low energies. Maybe there's something very interesting thinking that through. But what I'm saying is that that's what he's doing is more or less traditional effective field theory, right? And he's finding that this traditional effective field theory will violate unitarity and this growth unless the classical theory is very rigid. Right, higher derivative terms are suppressed in a way that go to zero when you take that UV scale to zero. So that's another way of thinking of it, and not very different somehow. Because once again, it's a growth condition that's giving you all the fun. I mean, I think if Simon were to take his growth condition and replace it by s to the 10, then he would have a lot of leeway.
Anyway, I think we should all probably go for lunch. But,
yeah. Okay. Sorry for giving a clear answer.
Yeah.
Okay. See you.
So yeah, see you, Shiraz. Bye. See you.